Bonjour à toutes et tous. Good morning, everyone. We switch to English. Welcome to our webinar this morning on the cooperation opportunities we certainly have between France and Israel in the field of green hydrogen for the aviation sector. My name is Thilo Schönfeld, and I'm in charge for the international affairs at the French Innovation Cluster, Aerospace Valley, here in the southwest of France. Our webinar this morning is co-organized with our partners from Israel and will be essentially moderated by Ariel Dici of the Business France office in Tel Aviv. And he will introduce us the different partners involved in the preparation of this event. But before I will hand over the mic to Ariel, here a few quick general rules relative to this GoToWebinar tool. By default, all the micros are muted and cameras are switched off, but you can ask your questions via the green toolbox on the right-hand side of your screen. Ariel and myself will then read and transfer your questions to the different speakers. Finally, the session will be recorded and the video will be available within a few days via our YouTube channel of Aerospace Valley. And most of the presentations will be available to all of the participants that have registered and that will participate. Thanks again for your interest, and Ariel, the floor is yours.
Oh, thank you very much, Thilo, and thank you to Aerospace Valley for hosting this webinar. We have a wide French and Israeli audience today. I will have the pleasure to moderate this webinar with a prestigious panel of speakers. We'll be together for a couple of hours, here you agree? So why did we choose this topic? The world is facing the major challenge of climate change, as you know, and to achieve the energy transformation, it requires a shift in electricity generation from fossil fuels to renewable energy and greater energy efficiency, notably. We held last year, together with our partners of the France-Israel Foundation, a webinar about green transition in the two countries, but focused on solar energy. We then also made a webinar addressed to the Aerospace Valley members to introduce them with the Israeli aerospace market. So today, we'll be talking about green hydrogen applied for aviation, thanks to the support of the Aerospace Valley cluster in the southwest of France, the main aerospace cluster in the country. According to the International Council on Clean Transportation, a third of all flights could run on liquid green hydrogen by 2050, while the global green hydrogen market will grow consistently. So green hydrogen can provide a link between growing and sustainable renewable electricity generation and the hard-to-electrify sector, according to a study from the International Renewable Energy Agency. Well, we have both in France and in Israel observed in the last couple of years a will to accelerate the policies and research focused on hydrogen to decarbonize the electricity sector in general and that of mobility in particular. Support from the state, innovative technologies and projects are growing, and we'll hear about all that from our institutional, scientists and business speakers from Israel and France, and have a few key understanding points regarding cooperation opportunities. You shall all have received the agenda of this meeting. We'll start with opening speeches from our partners and distinguished guests, and then hold 3 panels. The first panel, as you can see on the screen, will present the situation and state of the art of R&D of green hydrogen in Israel and in the French Occitanie region. The second panel will be devoted to scientific research, where Israel researchers and French researchers will present their work. And the third panel will be devoted to the presentation of 7 Israeli and French companies of their industrial achievements. We'll finish with a presentation by Airbus Zero Emissions, so stay tuned. We'll have a Q&A session at the end of each panel, so don't hesitate, like Thilo mentioned, to ask your question in the chat box. Let's start then. With short opening speeches, I will ask the introduction speakers to open their cameras and to share the cameras with us. First in line, we have Dr. Muriel Chaim, President of the Bi-State France-Israel Foundation, aiming to strengthen the ties in all segments of the civil society between our two countries, and initiator and co-organizer of this webinar. Muriel, please.
So thank you, Ariel. Good morning. Mrs. Aude Guivarch, General Manager of Business France in Israel, Mr. Bruno Darboux, President of Aerospace Valley, Mr. Daniel Sayag, President of the France-Israel Midi-Pyrénées Chamber of Commerce, dear participant to a webinar. The France-Israel Foundation was created in 2005 by the willingness of President Chirac and Prime Minister Sharon to bring together the French and Israel civil societies in different domains, should it be scientific, economic, or cultural. The different topics of the webinar are chosen according to the expertise of the region and their counterparts in Israel in order to create a partnership. Today's topic is green hydrogen, which is a universal one requiring enormous scientific, industrial, and financial commitments. France and Israel are developing their own national programs separately. We believe that this webinar will allow us to present very quickly what is done in scientific research and in the industry of each country, hoping this will lead to future cooperation. Thank you very much.
So thank you, Muriel. And I add on that my greetings to Gad Cohen and David Harari, two ex-senior executives of IAI, Israel Aerospace Industry, with whom we work on these webinar organizations. Now we're going to turn to our second partner and digital host for today, and we are happy to have the president of the Aerospace Valley cluster with us, Mr. Bruno Darboux. Bruno, you can start if you agree.
Absolutely. So welcome everybody to this webinar. I think this is an excellent opportunity to go beyond our southwest of France territory, which Aerospace Valley is dealing with, as you know. Our mission as a cluster is to boost innovation and to boost the development of the both aeronautics and the space sectors in the southwest of France. But obviously, we are playing not only in southwest of France, we are playing for the world. So we have a supply chain which is worldwide. And obviously our markets are worldwide. And we are embarked in the big transformation of the world. As you know, aviation is very much looking for its future, which is net zero emissions, and it's not an easy path. So we welcome any open debate, open thinking, and exchanges with whoever is willing to help us accelerate the transformation. So I think this is part of the events that help us accelerate transformation, which is very good. What I can tell is that for the aviation sector, hydrogen is the future. It's not the only path in the short term, in mid-term, but if you think long term for aviation, we need hydrogen. It will be used through different forms on board the airplanes. It can be liquid hydrogen directly under cryogenic storage. It can be gaseous hydrogen. It can be hydrogen built into power to liquid fuels. But at the end of the day, aviation with its net zero future needs hydrogen. So, okay, what can we do together? Our purpose here today and our purpose as a cluster is to accelerate what we can on technologies, fundamental research, yes, but more technologies. And for hydrogen, it's not only onboard technologies, it's also distribution of hydrogen and at the end of the day, production of green hydrogen upstream. So any exchange that will help us boost our research roadmap, any idea for proof of concepts that would demonstrate feasibility, and any idea for deployment at scale is welcome. And I think that we can say we are backed by a lot of public stakeholders that expect us to move fast on those topics at national levels, European level as well, but also regional level. We play with Région Occitanie and Région Nouvelle-Aquitaine, a very tense plan towards more hydrogen on the territory to serve various mobility needs, including aviation. So thanks for this workshop this morning. Now we'll be listening carefully to what you do.
So thank you very much, Bruno. However, it is written Laurent Bizio on your screen, but it is Bruno Darboux, the president of the Aerospace Valley. We'll have the chance to listen as well to Laurent Bizio, who contributed also a lot to this webinar in a few minutes. So before getting into the presentations, we have two last opening remarks on a commercial note. I invite Aude Guivarch, Director of Business France in Israel, to give a few words, and then Daniel Sayag, the President of the France-Israel Chamber of Commerce in Midi-Pyrénées, Toulouse. Aude, go ahead, please.
Good morning, everyone. I hope you hear me. I just clicked on the micro. Yes. Okay. So good morning, everyone. My name is Aude Guivarch. So I'm the Managing Director of Business France Israel. So I first would like to thank our partners, the Cluster Aerospace Valley, the France-Israel Foundation, and the Chamber of Commerce Israel-France in the Midi-Pyrénées. So the subject of the webinar today belongs to the most trendy topics of today. It's not only in the plan France 2030 of President Macron, but also here in Israel, where targets in terms of sustainability solution have been set for 2030, with a huge acceleration since the COP26. I want also to say a couple of words about Business France. So Business France is present in 65 countries around the world. We are responsible for helping French, mainly SMEs and startups, but also big groups to develop on international markets. And we are here also to attract foreign investments to France. So we arrange different programs during the year that can help companies as individual entities, but we also organize collective missions on topics that are important in the countries where we have offices. And this year in Israel, we have two main programs in the sector that Ariel Dici is managing. There is the program Tech for Change, which is an acceleration program aimed for startups, but also for SMEs that have innovation parts in their organization. It's in two verticals, the climate change and longevity, and we have the French Aerospace Days, sorry. The applications for those two programs are still open, but not for long. So if you want to have some details about these two programs, you're very welcome to contact Ariel or to contact me. So once again, we're very happy to participate to this webinar. It's very important for us to keep the communication and the opportunities on the floor on any occasion we can have to communicate with French companies, but also with our Israeli partners. Thank you very much.
So thank you, Aude, and Daniel, please.
Bonjour to all. First of all, perhaps I will repeat some words that have been already said. I would like to say that I'm happy and very proud to participate to this workshop. First, I would like to thank the Foundation France Israel, Aerospace Valley, and Business France to have organized such a webinar, and perhaps remind the mission of the Chamber of Commerce France Israel. Our job, let's say, our mission is to support the business relationship between the ecosystem in Israel and the ecosystem in Occitania region in France or around Toulouse. I think all of us, we know or we have heard about the vitality of Israel in terms of startup, innovation, high-tech, and so on. And it seems, or we see that Israel became a relevant player in several areas, several regions especially in space and aeronautics. So I'm speaking this morning with my position of President of the Chamber of France-Israel, but I have also in the real life, I'm working for Airbus, like many people in Toulouse, and I know the position that Israel is taking in the area of space and aeronautics. And that means that when some players are becoming so relevant, I think it's a good, the next step is to know each other, and our mission as a Chamber of Commerce, and I think this workshop will help, is to help people to know better what happened in the area of business, but also in the R&D and the institutional. It's the first step. I would like to do a comment there. The current crisis, let's say, has promoted the use of the digital tools, and obviously, thanks to those digital tools, we can do such events like that, and we can really exchange information. We can really know each other. We can really discover what happened. And I hope all the participants will enjoy and discover and learn. And I would like to say thank you to everyone and have a good webinar. Thank you.
So thank you very much, Daniel. So let's now enter our first panel, focusing on the situation and state of the art of R&D of green hydrogen in Israel in the French Occitanie region. I will ask Dr. Gideon Friedman, Benjamin Febvre, and Laurent Bizio to open their camera with us, as they are the speakers of the first panel. So we'll start our presentation with Israel. Israel aims of reducing by 27% of its gas emission until 2030 and 85% by 2050 compared to the levels of 2015, known as the COP21, which took place in Paris. During the last Elat Renewable Energy Conference in December, I heard, and maybe your backup, you'll correct me, Gideon, that the Energy Ministry was planning to spend around $30 million over 5 years on the National Institute for Hydrogen Production and Storage. So Dr. Gideon Friedman, you are the chief scientist of the Israeli Ministry of Energy, and you will tell us more about Israel's policy regarding green hydrogen and how Israel intends to transform the future of energy. Please, Dr. Friedman. We just can't hear you. Maybe open your mic. And I know you speak French as well now. So bonjour.
Good morning, everyone. It is a pleasure to participate in this joint webinar of France and Israel to talk about green hydrogen with the emphasis on the aerospace industry. For us, we are in the early stages of adopting hydrogen. So we are not yet into aerospace, which is really probably the most challenging field for hydrogen. I will discuss generally the situation in Israel, the policy for green hydrogen in Israel, as much as I can. I have a relatively short time, and I already apologize that I will have I have to leave, and someone here, Dr. Shachar Dolev, will be happy to answer the questions that you have later on in this panel. I may join you later, but I must leave, so I apologize for that ahead of time.
Thank you. No problem. Just say next. Sorry, Gideon. Just say next. I will switch slide. Okay. Thank you.
So for Israel, the situation is a little different compared to other countries. Every country has its own story, of course. In terms of CO2 emissions, which are the main initiative, the driver for the transformation in the energy market. Israel has a very large electricity segment with about 60% of the CO2 emissions from electricity and then transport. The industrial sector in Israel is smaller, which is how we try to target our goals. Next slide, please. So our first goal is really the electricity market and the transportation market. In terms of the way I view hydrogen, I like to separate it into 3 segments: the hydrogen generation, hydrogen storage, and transportation which are called logistics here, and then the hydrogen use either directly as hydrogen, like in a turbine to generate electricity, or to generate heat from hydrogen, or through fuel cell to generate electricity again. So it's in a sense a cycle, but 3 segments. The challenges in the hydrogen and the green hydrogen market are very significant still. First of all, there are costs in all 3 segments. The costs are high and not yet competitive. The logistics issue is a big issue. It's a very problematic, as mentioned already. Hydrogen in aerospace, for example, can be liquid hydrogen, can be through a carrier or through compressed gas, but all of these have challenges in the logistics. And finally, there is a very fundamental issue of the efficiency. So if we look at the whole cycle, the efficiency today of the whole cycle is around 30%, which is in many ways, in terms of sustainability, it's unacceptable that we will throw away 2/3 of the energy. So we need to resolve all of these before hydrogen becomes a mainstream partner in the energy market. Next slide, please. I will now again delve a little bit into the special story of Israel. And Israel is a small economy. So this means that Israel will not determine the market trends in hydrogen nor in any other markets. If the world goes to a specific solution, to hydrogen, Israel, of course, will follow. And this means that we will not be leaders in setting the trends. We cannot be, even if we think that one solution is the correct solution, it's meaningless. The world will determine the larger countries. Israel is also a small country, so this has 2 implications. One, that for transportation, land transportation, potentially we don't need such long range solutions. We can probably do with shorter range solutions. And also, as we are a small country in geographically, so I will talk about it a little bit in terms of our renewable energy, which is solar and requires a lot of land. We have a smaller industrial sector, as I mentioned, and we have today large natural gas reserves. I will mention this. I mention this because to generate hydrogen from electricity, from renewable electricity, takes about 10 times the energy compared to generated from natural gas. Of course, we don't want the emissions from the natural gas generation. However, we do think there is a midway in the sense that we are looking for technologies to generate hydrogen from natural gas without emissions. And this will be, I think, at least a temporary solution until the hydrogen market becomes mature enough and all the challenges are addressed. We have almost exclusively solar energy here in Israel, very little wind in terms of renewables. I already mentioned the difficulty of the size of Israel because solar energy requires quite a lot of land. So this is one challenge. And of course, solar energy is only available in Israel for about 1,700 hours per year, which is a capacity factor of 20%. Of course, it's much nicer than most of France, but still there are many hours where we need to find a solution and we need to store the energy. Basically, can be also in hydrogen, of course. We have a strong innovation system, so we want to take part in the hydrogen revolution, the green hydrogen. We want to provide technologies to address the challenges that I mentioned. And we also have geopolitical considerations like our neighbors, which are also very sunny and also with large land potential. So we are looking to collaborate with them. And also we have special resilience needs. So for us, backup is very important. Again, this means that hydrogen is a good candidate to provide this resilience. Next slide, please. in terms of hydrogen, so after I showed you the considerations, what are our conclusions from that? So first of all, we want to invest quite large efforts into R&D. We want to participate in the technologies, in providing the technologies for the transformation of energy and of course hydrogen as well. We want to be part of the hydrogen game in the sense that we want to be state of the art. We will start with the heavy transport. We will adopt interesting special use cases where hydrogen is already a good solution today. And we need to address our industrial sector, although small, but we need to find solutions there. And hydrogen is again a good player there. We will invest in blue hydrogen as much as we can, or turquoise even, some if you are familiar with this term. And we will also want to prepare our system, our natural gas transport system to hydrogen. Of course, we want to do international collaboration. We know we are dependent on that, both with our close neighbors and with Europe. And we have both plans for an electricity connection through Cyprus and Greece, and also originally a natural gas pipeline. But I'm sure that this pipeline will also be capable of transporting hydrogen in the future, whenever, if it's built. A few interesting events and steps that we are currently taking. We are supporting essentially 2 refueling stations for hydrogen. They are in construction, hopefully will open this year. In one of them will be a portable station, so it will be able to travel around and provide hydrogen where needed. We want to import the heavy transportation, so we are supporting as a ministry we're subsidizing essentially the buses, trucks, and heavy transportation that will run on hydrogen, and so that we are experienced with using hydrogen. And we are developing an intercity bus on hydrogen. This is not a tremendous innovation, but just adapting a bus to intercity, because we feel that this is where hydrogen has an advantage. We have several interesting startups, H2 Pro, which will be here later. And I mentioned already that we want to transform natural gas to hydrogen. So we are supporting hydrogen pyrolysis research. And we are doing hydrogen storage underground. We are doing a new survey of the underground of Israel for storage and for CO2 storage, but also for hydrogen storage potentially. We did actually update our 2050 plan to 0, at least unofficially. We will do the official changes, I expect, this year. So we are targeting 0 emissions. I will stop here because my time is up. The presentation, which is longer and has some of the companies that provide innovation in hydrogen, will be available to anyone who wants. Thank you.
So thank you very much, Gideon. Yes, we'll share your presentation with the audience as well. Thank you for sharing Israel's challenges and ambitious perspectives. We'll continue discussing green hydrogen development policies by turning to the east side of the Mediterranean Sea. And before turning to Benjamin Febvre, just wanted to remind you that you can ask your questions in the chat box, and Thilo Schenfeld and myself will ask them to the panel. So feel free to do so. Mr. Benjamin Febvre, you are the coordinator of the hydrogen sector in the Occitania region. On a national level, France intends to become world leader in green hydrogen. A 2 billion euros envelope was budgeted as part of the strategy for the development of low carbon hydrogen. So how do you implement it in your region? And you have about 10 minutes. Thank you.
Thank you, Ariel, and thank you to give me the opportunity to present you what happened in Occitanie around hydrogen. Just to be very precise, this 2 billion euros is in addition to 7 first billion euros. So we've got a huge plan around 9 billion euros at the French scale to become an international leader and develop green hydrogen production and also heavy duty transport around hydrogen, help the innovation, etc. So we want to take part of this development, and we started to develop it in 2016. I'm just to present myself. I'm the hydrogen sector coordinator. I'm working for Adoc, with business development and economy development agency in Occitanie region. And for those who don't know where is Occitanie, it's the region between Pyrenees Mountain and Mediterranean Sea, including the two metropoles of Montpellier and Toulouse. Next slide, please. Here you have a timeline. We present you what we did and what we are going to do in hydrogen sector. As I said before, we started in 2016 with a large study, and we identified that hydrogen is a real subject for us, and we have the potential to create a real industrial sector. Industrial sector because we've got a lot of actors who are working on hydrogen, like company, like laboratories, for example, but also because we have the potential to produce green hydrogen, because we are one of the French region who have the biggest potential in sustainable and renewable energy production. So we create a coordination tool named IDEO, for Hydrogen Development Occitanie, financed by the environmental agency, national agency, and the region Occitanie, and to develop and make this sector a reality, and help all the actors to generate projects and help to coordinate this sector and become a real industrial sector. It was in January 2018, so 4 years ago. In 2019, the Occitanie region launched a support plant only dedicated to green hydrogen, with 150 million euros over the 10 next years. Today, it's still the biggest plan and the more important plan around hydrogen at a region scale in France, and we want to help the development of technology and the deployment of these technologies. Also, we want to generate a huge project, and also because it's a region skilled, we want to anticipate and help for the development of the anticipation of skills of training to help the companies and laboratories to recruit. We've got some objective in 2030. We want to deploy hydrogen train. We got an objective of deployment in 2024. More than 50 hydrogen refueling station, 2 hydrogen production plants. It's a green hydrogen production plant, and also help the purchase of more than 3,000 vehicles using hydrogen as fuel. It's a part of our global climate and energy strategy to become a territory who produce the same quantity of energy that we consume. And hydrogen is a real help for this, because it's a possibility to convert and store renewable energy, and to use it to decarbonize mobility, industry, building, for example. Just to give you the 2 last points, it's we launching a regional roadmap around that subject of jobs and skills, and also we create a global group of research and development around hydrogen in Occitanie named RIO, but I will speak just after. Next slide, please. The Occitanie and all the administrative region in France have some mission. One of this mission is the development and the coordination of transport in the region. Also, we lead and we drive the main ports in the region. So we identified that the use of hydrogen is a key factor of development, and where it's possible, we want to generate a hydrogen consumption. Is the reason that the region invests on 3 trains, hydrogen trains. We want to put in the Pyrenees mountain in a line, generate the consumption of 62 tons of hydrogen per year. We want also, and we are developing a hydrogen dredge for the harbor of Sète and Port-la-Nouvelle. We will be able to consume 72 tons of hydrogen per year. Also, we are working with the company Safra with the retrofitted of 15 coaches. And we have a huge project supported by the European Union with a budget of 110 million euros in global to deploy at the same time 2 green hydrogen production sites, 7 refueling stations for trucks, and 40 trucks, 62 refrigerated units for trucks. The name of this project is H2 Corridor. We also help the deployment of infrastructure. For example, we take part of the iPort project. We will be start in this year, and we are developing and deploy a 1 megawatt electrolyzer in the airport of Toulouse, and the second deployment will be in the airport of Tarbes in the Pyrenees mountain. At the same time, we invest in a huge production site with 50 megawatts of capacity of electrolysis in Port-la-Nouvelle, near from the Mediterranean Sea. It's very important because it's opened the way to a green and competitive hydrogen production. Also, we helped the work on the efficiency and the development of new technology around hydrogen by investing in the company Genvia with a joint venture between the CEA laboratory and the company Schlumberger, and they want to develop in the city of Béziers a gigafactory to produce a new electrolysis system using the solid oxide in high temperature electrolysis. To finish, we've got a project.
France webinar for aerospace.
Because there is a mic open.
Very important then.
Just if the person speaking can close his mic. Thank you.
Okay, just I continue. We invest also in a gathering of 4 laboratories in the city of Toulouse, in the campus, technology campus around hydrogen in the ex-airport of Francazal, with 12,000 square meters dedicated to R&D around hydrogen and help of the deployment of hydrogen plane, but also other use of hydrogen. Next slide, please. I will not detail all the logo you can see here, but you have an overview of all the actors who are working on hydrogen and propose a technology, services around the hydrogen. You've got the one who develop technology, where the industrial value chain from components to integrator. As you can see, there are some logo of people who are present today and will present their product and services. You've got also the supply chain from production to use of hydrogen. You've got the academics lab who are today gathering around the research hydrogen Occitanie named RIO Paul. And also all the services and support with engineering, marketing, training, safety, financial, etc. And the clustering, including Aerospace Valley, that we are working with Laurent Vizio to develop aviation application for hydrogen. In the global scale, IDO, it's more than 80 actors who are working on hydrogen in Occitanie. And if I put it on a map, it's the next slide, please. You've got here the main project with a color code. The blue one are the industrial project to develop and industrialize hydrogen technology. The orange one are the infrastructure of production and of refueling, and the green one are the use when we're leaving the diesel consumption for green hydrogen consumption. So you've got an overview of what happened in Occitanie. I hope it was very clear for you and very helpful. And I'm pretty sure when I see the next intervention, you will have the detail that my presentation missed. Thank you very much.
So thank you very much, Benjamin Febvre. So indeed, it was clear. We understand there is a healthy competition as well in Europe to handle energy performance targets. And your demonstration shows the Occitanie region's strategy to position itself at the forefront. And with Laurent Bizio, as you mentioned, we'll take it down now to the aviation applications. So Laurent is also one of the main organizers of this webinar. At the Aerospace Valley cluster, you have a dedicated ecosystem on propulsion and embedded energy that you pilot. I told in the introduction that a third of all flights could run on liquid green hydrogen by 2050, for instance. Could you tell us how you conceive your ecosystem's role and objectives within Aerospace Valley, within the background of the decarbonation of the industry? Green hydrogen can be an alternative fuel for aircrafts, for thermal engines. What are the opportunities you see in the future? Thank you, Laurent. So just we can't hear you. If you just open your mic.
Yeah.
Thanks.
Yeah.
Great.
Thank you for this introduction, Ariel. I will try to tell you what will be the future for propulsions.
Listening.
So, for Aerospace Valley organization, it's quite simple. We have 3 different strategic sectors. As you probably know, Aerospace Valley is the main competitive cluster in terms of aerospace activities. And for that, we have activities on aeronautics, space, and also drones. To support these different sectors, we have 5 family skills, I would say, that what we call the ecosystems. And one of these 5 ecosystems is the propulsion and embedded energy, the one on which I'm working on. So I will detail you what are the activity inside this ecosystem. First, Aerospace Valley has the chance to it's not exactly a chance. It's the results of several years of work. We have more than 800 members in this organization, and the members are industrial companies, small companies, and also large companies. We have some representatives today in the webinar that will present their activity, and we are working together like H3 Dynamics, or we have also Libera Aerospace or Airbus. We have also some academic members like labs and schools and university. One of their representative is, for instance, H2 Pulse that we will hear next, and also institutions. We are working with them, and other cluster, and for instance, IDO, which Benjamin presents us, is one of them. So we organize some events like this webinar, or some coffee techno, or request for interest, and we send it to our members. We catch from our members all the innovative concept that they want to develop, and we make the link. We create the link between them to create some collaborative projects and to develop new innovations. As soon as we have this collaborative project, we help members to develop their market, and that can be new markets, local markets, and also international markets with this new innovation systems that we can develop together. Another aspect of the Aerospace Valley cluster is to help also members to access to fundings. When we create the collaborative projects, we give them access to public fundings at different level, regional, national, or also European, and we can help them also for the private fundings. So what are the technology that we are working on inside the ecosystem, propulsion ecosystem? We are working with the new fuels that will help us to have a greener aviation. So we are talking about new sustainable aircraft fuels, and also the hydrogen is also a new fuel. In terms of hardware, we are working on the powertrains, of course. So it's similar to the industry of automotive industries, where we are talking about hybridization, where we mix thermal engines technology with electrical engines. We have also the full electric powertrain possibility, and next we are taking into account the fuel cell integration inside the aircraft. So all of this technology, we have to keep in mind that it's not a competition between technology. It's all this technology, we work in parallel. Members are working in parallel in this technology. There will not be a winner at the end. All of this one will be used. It will depend on the application that we will have for the application that we are talking about. So in parallel of this development, we have to work also on different sectors, different work package that are not directly the greener aviation, but it's linked to the greener aviation. For instance, if we are talking about a single engine aircraft with propeller, we imagine to modify it with e-motor, so we will reduce the noise of the engine. But if we stop the development at this point, we'll have the half of the development, because at the end the aircraft will still be noisy because the propeller is noisy. So in parallel, we have to work on the quieter propeller. And same for the structure. We have to work on lighter structure and recycled structure at the same time of the powertrain innovation. So with new material, we can access to that. If I focus on the hydrogen technologies, we have a lot of barriers to solve. First, we have to think about how to implement the hydrogen tank inside the aircraft. So depends if it is gas hydrogen or liquid hydrogen. With the gas, we have to manage the very high pressure, so more than 700 bars. And if we are talking about liquid hydrogen, we have to manage some temperature as low as the minus 250 degrees, so which is quite very low. So technologies are dependent of this this pressure and temperature. Of course, we have to take into account the safety and the regulation, and they have to be also created because it's a new technology. As soon as we have the hydrogen on the aircraft, that's a good point. But next is how do we use it? So two ways to use the hydrogen inside an aircraft. First one is to use it through conventional thermal systems, so like a gas turbine or internal combustion engine, and we have just to modify them to burn hydrogen. That's the first way. Another way is to use the hydrogen through the fuel cells. So the fuel cell is generated electricity. So for electrical propulsion, that's good, but it also dissipates a lot of thermal energy. So we have all the thermal management to manage inside the aircraft when we are talking about fuel cells, and they are mixed with batteries technology and also all the management with the battery safety. When we have the aircraft flying with hydrogen, we are happy, but that's not the end, because we have to refuel it at the gate with hydrogen. So we have to think about infrastructures and to know how we store hydrogen on the airport, and in which state, is it liquid or gas, and then is it produced on site or outside. So all of these technological barriers have to be solved in the next few years, in the next few months, I would say. And for that, we will urgently need new skills and new jobs. So that's the reason why Aerospace Valley is working also with academics to modify and to implement new training programs in line with these technologies. So this slide just to tell you that the new propulsion systems are not only papers, it's reality today. In Occitanie region and the Nouvelle-Aquitaine region, we have a lot of players, and there are small ones, but also larger ones, and they all propose some new demonstrators. And in the next few years, we will have a lot of solutions deployed. And what we think in Aerospace Valley is that light aircraft can be a very interesting and innovative laboratory as a pre-chamber of commercial aviation systems, and as a demonstrator of new technology and the return of experience for the commercial aviation. And it's the way, that's the reason why we create a MILE initiative 1 year ago, and now we have more than 300 members inside this community for MILE. And we think that with this initiative, we can develop technology very quick, in a quick way, because it's on smaller aircraft, so development delay are very short, and with a reduced cost to access to this new technology. So
thank you, Laurent.
We are very happy to develop this new chapter of the aeronautics. Thank you.
Thank you very much, Laurent. And let's take a few questions maybe from the audience before we turn to our second panel. So Thilo and I will be looking for your questions. There was maybe a first question to Gideon Friedman, if you can put back your camera on. The first question was, hi. The first question was to precise the strategy regarding hydrogen. The question is there any hydrogen strategy in Israel to be released, global strategy? I mean, Gideon mentioned a few investments. Is there a global strategy to be released? We can't hear you.
Hi, my name is Shachar, and I will be replacing Gideon for the Q&As. So the strategy in general is quite local. We are, as Gideon said, we have several pilots here and the initial phases of a refueling station, etc. Apart from pushing forward the academy and the companies for innovation, we don't have any global strategy per se.
Okay, thank you. Thilo, do we have other questions you see? Maybe for Benjamin or Laurent? I see maybe for Laurent a question here regarding the last slide you mentioned. Is the MAEL initiative open to international partnerships?
Yeah, MAEL initiative is open for members of Aerospace Valley, and it's a good point. In our members, through our 800 members, we have members who are outside the Occitanie region and Nouvelle-Aquitaine region. So yes, it's possible to have other members outside the territory, southwest territory of France.
Okay, great, thank you. And for Mr. Benjamin Febvre, if you are still here, can you give more information? You mentioned the RIO research group. Can you give more information regarding the research group and on the techno campus dedicated to the hydrogen technologies? We just can't hear you as well. Maybe just open your mic again. Not yet. Last tentative. Yeah, so I switch back to you maybe later on. And before we'll go to our second panel, and then I'll ask the question again after the second panel ends. So thank you very much to all our panel one speakers, and now to our second panel.
Sorry,
yeah,
just a minute.
Please.
I would like to add, maybe I was not explaining myself very good. Although we don't have a strategy, we'll be very happy for cooperation, international cooperation on R&D and pilots in relation to hydrogen and aviation, of course, although we don't have a concrete strategy. Thank you.
Great, thank you very much, and we'll follow up on that, obviously. And so our second panel will be devoted to Israel and France scientific research. Renewable hydrogen is currently expensive, right? But costs are coming down. Over 95% of hydrogen is still made using fossil fuels, but hydrogen can also be produced cleanly using renewable electricity to split water in an electrolyzer. With the cost of wind and solar continuing to fall, the question is whether the cost for electrolyzers and renewable hydrogen can follow. Why do I mention that? We have with us Dr. Avner Rothschild. You're a professor of material science and engineering at the Technion, Israel Institute of Technology, researching electrochemical materials and devices for green hydrogen production, and you will speak about the invention of Adoc water electrolysis. So please, Professor.
Yes, so thank you very much. Can I share my screen? Okay, you have this already.
Yeah.
Okay, so in this 10 minutes presentation, I'll kind of walk you through the science behind the innovation of a new water electrolysis technology that is now being commercial by the company H2Pro, which will be presented by Dr. Chen Dotan, who was one of the inventors of the technology and now is the CTO of the company. So this work is a joint work between my group at the Material Science Department and Professor Gideon Grader at the Chemical Engineering Department of the Technion. Next slide, please. So next slide. Okay. So here on the, the one before. Okay. So this is kind of the basics of the technology in comparison to the conventional electrolysis, in this case, low temperature electrolysis or either alkaline or PEM, where that is shown on the figure on the top left, where you see that essentially what you have there is a quite complex structure, but what actually does the work is in the center of this of the device you have an electrochemical cell comprising of two electrodes, anode and cathode, and a membrane that separates the products, hydrogen that produced on the cathode and hydrogen at the anode. We call this coupled electrolysis because the two reactions that generate hydrogen and oxygen are coupled in both time and space, meaning they occur at the same time, nearly at the same place. Therefore, you need the membrane and all the sealing and all the plates that make sure that you can separate the hydrogen from the oxygen. Our technology or our process, which we call ETAC, short for electrochemical thermally activated chemical process, is completely different. We don't have a membrane. We decouple the hydrogen and oxygen evolution reactions as shown on the bottom left image, where now we produce them in two different stages, such that in the first stage, we produce hydrogen at the cathode, just like in normal electrolysis, but at the anode, we do something completely different. We charge, basically it's kind of a battery electrode, we charge an electrode and nickel hydroxide into nickel hydroxide. Then we change the electrolyte from low temperature electrolyte or room temperature electrolyte to high temperature electrolyte of close to the boiling temperature of water. And then there is a spontaneous reaction between the charged electrode, the charged anode, and oxygen, and water that generate oxygen spontaneously without applying electricity. And the electrode regenerate to the initial stage, and then we can run another cycle and another cycle, and we can run many, many tens of thousands of cycles because this reaction is completely reversible. So that's on the basic cell level. If you look at the system, that's the figure on the right side. So each and every one of these cells is connected to three reservoirs. One has the hot electrolyte that generates oxygen. The other one has a cold electrolyte where we generate hydrogen, and we have a kind of a washing electrolyte to wash between the stages that is at an intermediate temperature. So this innovation was made by Chen Dotan and Avigai Landman, then students in our groups, and was published in this article in Nature Energy about 3 years ago. Next slide, please. Okay, so the main advantage of the technology is the first one. Yes, this one. The first advantage is in the structure of the cell. Because we don't have membrane, we can now generate, and we don't need the ceilings because we generate hydrogen and oxygen in different stages, in different times. We can now have a way to a completely different architecture where we put the electrodes one on top of the other with some very simple separator between them, and then roll them up. Then we have a rolled electrode set that we can pile like shown in the figure on the right, and this saves us a lot of space. So it's a very compact and very efficient design of the electrolysis, unlike a conventional electrolysis, which is shown on the bottom, which is a planar structure with a lot of, basically a lot of metallic plate that both cost a lot of money and also a lot of weight. So essentially our design is much more compact and lightweight, and that turns out to be some very advantages in terms of the logistics of transferring systems to the customer. Next slide, please. The other advantage comes from high efficiency. So because we divide the process into two steps, we actually divide the oxygen evolution reaction into two steps in a way that is much more efficient and allow us to do our process at an average voltage of 1.5 volt, at the cell voltage of 1.5 volt, whereas other electrolyzers, except for the high temperature one, which is a different story, But all the low temperature electrolyzers, both alkaline and PEM and AEM, operate at voltages above 1.8 and often above 2 volts. So we can save a lot of energy, and our cell efficiency is close to 99%. And we expect that at the system level, we will be able to deliver more than 90%, perhaps even more than 95%. Next slide, please. So here I explain very briefly the reason why the process is so efficiently. So first I saw the conventional oxygen evolution reaction in conventional electrolyzer. So this is the 4-step reaction where the reactions are shown both on the left and on the right sides of the slide, where each and every one of these individual steps, so these are chemical or electrochemical charge transfer steps that occur at a single atomic site at the surface of the electrode, whereas the rest of the electrode remains completely inert. What happens is that we involve here at the metallic site, say nickel, you change the intermediate states, you change the species, the chemical species that are bonded into this reaction site in 4 different steps. Next slide, please. So if each and every one of these steps was identical, we would not have the so-called overpotential, which is the main reasons for the efficiency losses in conventional electrolyzers. And that is shown on the top right figure in the red curve. So if all of these 4 steps were identical, we would have no overpotential loss. Unfortunately, because there are 4 different species that are connected to this metallic site, they are never identical, which means that some of the reaction will be easier than the other, and then other one would have to be more difficult because the overall of the 4 steps is identical. And this is the reason for the overpotential loss of at least 0.4 volt, which degrade the efficiency of all of the conventional electrolyzers. So that is the standard electrolyzers. Now in the next slide, we'll show what we do in our case. So here you can see that in our case, we split this reaction into 2 stages. The first stage, we charge a nickel hydroxide electrode into nickel oxyhydroxide by a series of 1 electron per site charge transfer reaction. So instead of 4 electrons per site, here we have 4 electrons per 4 sites, or 1 electron per 1 site reactions. And then we release the charge in a chemical reaction of the charged electrode that returns back to the discharged electrode, but that's a chemical reaction that does not involve any electricity. So essentially, we replace a 4 electron per site reaction by 1 electron per site per 1 site reaction, and that is much more easy for the reaction to proceed, and that essentially reduces the overpotential from above 0.5 volt to a much lower value of about 0.2, perhaps even lower values. And that's what enables us to reach this very high efficiencies. Next slide, please. So this electrode that we're using is based on the nickel hydroxide, nickel oxyhydroxide cycle that is not new. Okay, this cycle has been used in rechargeable alkaline batteries for nearly a century. So this is the same, at least the charging reaction is the same reaction that you have in nickel metal oxide, nickel metal hydride, nickel cadmium, and nickel hydrogen batteries. That the latter is probably the most reliable battery that was ever made. And the reason is because these batteries are the ones that are used in space missions such as the Hubble and other space missions, where they operate for many, many years. So this is a reversible reaction that allows us to run many tens of thousands of cycles. And the reason is because if you look at the atomic structure of this nickel hydroxide, you see that it is a layered structure where the hydrogens are connected to the oxygen and pointing up and down. And essentially the difference between the charge and discharge is how much of the site is occupied. In the discharge phase, all of the sites are occupied by hydrogen, and in the charge phase, only half of them are occupied. So that is the mechanism of the charging. And then the second reaction, the generate oxygen, is pretty much the opposite reaction, which occurs chemically. Next slide, please.
Last minute, Professor.
Okay, so we take special care of producing electrode in a very porous structure with fine internal structure that give rise to easy access of the products of the reaction and the reactants in and out. So we start with a porous nickel from substrate on which we grow our electrode, nickel hydroxide electrodes, by electrochemical deposition, and we have this fine structure. You can look at the bottom right image and you see that we have flakes of only a few nanometer in thickness that allow very fast mass and charge transfer in and out of the active region. Next slide. Yeah, so we started this work here at the Technion 6 or maybe 7 years ago. And here you see some typical slides of the tiny electrodes, 1 centimeter square electrodes, the electrochemical deposition system we use, and the manual process that our students were doing manually, moving from one cell to another. Today, it's a completely different process, one by an H2 Pro, where we have much larger electrodes and real systems, which you will hear more in by Chen Tan later today. Next slide, please. Yeah, so just I want to finish with acknowledgement to my partners, Gideon, Chen, and Abigail, who developed this technology, to my current group on the right side, Elena, David, Ilya, and Yossi. And funding for this research was received by ERC POC project and by the Ministry of Energy. So thank you very much.
Thank you, Toda Rabba, Professor Avner Rothschild. And I remember a year ago meeting with your associate, Professor Gideon Grader. We've got indeed amazing results regarding the electrolysis process. You mentioned over 90%, I guess, instead of 70 of its energy efficiency and reduction of the cost as well. And as you mentioned, we'll hear in a few minutes from the company H2 Pro that was founded based on this research. And now we'll turn to Dr. Nicolas Berthier. If you can open your mic and camera, please. Dr. Berthier, you're a special advisor at the French Aerospace Lab ONERA, which develop research activities in the aerospace field. You are in the energetic departments in the fields of numerical simulation and combustion. ONERA's representative for the regional key challenge, green hydrogen. What is your approach, Dr. Nicolas Berthier, to the existing challenges for aerospace systems? Can you hear me?
Yes, and do you hear me?
Yeah, we can hear you very well. We just can't see you.
Okay, so thank you very much. My presentation is focused on research at ONERA for H2 powered aircrafts. Next slide, please. Okay, to start my presentation, a brief reminder of the context. As everyone here knows, and as previously mentioned, Paris Agreement and increasingly stringent norms on air quality impose to find solutions to reduce CO2 emission and to improve air quality. For aeronautics, 3 ways are explored, such as sustainable aviation fuels, electrification, and of course, hydrogen, with 2-way, fuel cell, and combustion. In this presentation, we will focus on the use of H2 in aeronautics for combustion. Also, there are, of course, some common issues with the fuel cell, like storage, for example. Next slide. Now, a brief recall of H2 properties. The use of H2 provides great advantages compared to those of kerosene. Indeed, there are no carbon emissions, no CO2, no HC, no soot, no sulfur compounds. H2 owns a high specific energy, and H2 burns very quickly. But there are some properties that require care. H2 has a very low density, even in cryogenic state. There is possibly local high temperature and NOx emissions, a large release of H2O. H2 is very flammable and has a high diffusivity in metals. So new technologies based on the use of H2 will have to exploit its strong points and limit its drawbacks. Next slide. So the use of hydrogen for combustion in aircraft is a disruptive technology which impacts a large part of components. Therefore, to have a global vision of the problem, it's necessary to bring together a large range of skills like aerodynamics, energetics, materials, systems, which is the DNA of ONERA. If you look at the pictures on this slide, each of them illustrates a specific problem encountered with the use of hydrogen. From the left to the right, one of the greater challenge with hydrogen will be the storage, probably under cryogenic state in order to increase density with the use of large insulated tanks. Choice of shape of tanks, which has a great impact of the design of the aircraft, materials of tanks, metallic or composites, and insulation processes are major questions currently being studied. Then hydrogen will be led to the combustion chamber through an initiation circuit, which must be perfectly sealed, even at the level of the wells, because hydrogen is a very small molecule which can easily diffuse through metals. Along this injection line, safety is therefore a first order problem, with in particular the treatment of possible hydrogen leaks. There will also likely be a fast change of hydrogen from liquid phase to gaseous one during its transport between the tank and the combustion chamber. At last, there is the heat exchange question, because it could be interesting to use cold hydrogen to cool the air used for cooling some parts of the engine, like turbine blades, for example. Hydrogen will next enter the combustion chamber, be mixed with air coming from high pressure compressor outlets and burn. Hydrogen physical and chemical properties being very different from these of kerosene, combustion chamber and injection system will have to be redesigned. A brief focus on this point will be done in the next slide. After the combustion chamber, no, previous, wait, thank you. After the combustion chamber, yes, no, previous one, yeah, perfect, thank you. After the combustion chamber, hot gases enter the high pressure turbine stages and then low pressure turbine stages. For these parts of the engine, main questions are related to the impact of a large amount of gaseous water on heat exchanges between turbine blades and surrounding hot gases, on its chemical action on its metallic surface. At last, there are open questions concerning contrails formation. On one side, H2 combustion provide no particle, like soot, which are currently the main contrail precursors. But on the other side, there is a huge release of H2O vapor. We could be involved in other nucleation mechanisms, for example, with pollens. So there are currently a lot of open questions, and I suggest you to focus on one particular point, H2 combustion. Next slide. There is an extensive background at ONERA on H2 combustion for rocket propulsion. But conditions on rockets and air-breathing combustion chambers are different in terms of power or pressure, for example. But one of the most impacting features is that in rocket propulsion, O2 burns with H2, but there is no nitrogen. Therefore, temperatures are higher in a rocket combustion chamber, but above all, there is no risk to form nitrogen oxides. On the other hand, nitrogen oxides formation is of major concern for H2 air combustion chambers. Next slide. Therefore, we have been working at ONERA for more than a year on the conception of novel injection system for aircraft, which ensures combustion stability, which is a very important point, and very low NOx emissions. On the left of the slide, there is a movie of a numerical simulation result obtained with ONERA CEDAR code. And on the right, Mikado test rig, which will be soon be used to test this injector. These new injectors will be tested before the end of the year on our combustion benches at Palaiseau near Paris, or Faux-Gamouzac near Toulouse. Some of these benches could right now use a limited amount of hydrogen, and all Onera combustion rigs will be gradually updated in the next years to allow a common use of hydrogen. These transformations will be carried out in the framework of the DGAC Becar project. Next slide. Thank you. To finish, I would like to present you ID cards of two important projects related to hydrogen. The first one is Sirius H2 project, which is a DGAC project led by Onera with Airbus, Safran, and Dassault. Indeed, H2 combustion releases no particle, but a lot of water. So therefore, it's unclear whether the use of hydrogen lead to more or less contrails than today with the use of kerosene. There are two main goals of this project. The first one is to analyze formation and properties of contrails generated by H2 combustion. And the second one is to explore experimental means for in situ data acquisition. Next slide. And at last, Energia project, which purpose is mainly to build a shared vision. It's a DGAC project led by Onera with Airbus, Safran, and Dassault Aviation. Two goals. So, like I said, build a shared vision of energetics outlook for decarbonization solution and of plan analysis. There are some fuels, alternative fuels analyzed, such as biofuels, electrofuels, methane, and of course, hydrogen. Next slide. To conclude, H2 combustion could drastically reduce environmental footprint of air traffic. Second, physico-chemical properties of hydrogen are very different from those of kerosene and pose new scientific and technological questions. With both experimental benches and numerical codes, like SEDA, covering physical fields ranging from aerodynamics to materials and energetics, Onera can conduct multidisciplinary research on this new field. And at last, first promising results were obtained last year for new injection system. And very important point, for any questions concerning collaboration with Onera on H2 powered aircraft, please contact our director for aeronautics propulsion and environment, Philippe Novelli, philippe.novelli@onera.fr. Thank you for your attention.
Thank you very much, Dr. Nicolas Berthier, for explaining Onera's approach and the promising results you had last year. So we heard before about in Israel about the Technion breakthrough research in Israel. What with another famous university here, Professor David Zitoun will present the Bar-Ilan activity on hydrogen regarding material science research for production and use of green hydrogen. Please, Professor Zitoun.
Okay, thank you very much for organizing this very nice webinar. It's for me a pleasure to speak. I have to say that my journey to Israel began as a PhD student in Toulouse, and also I've been a senior lecturer in Montpellier. So I'm very proud to be a part of the Occitanie and also of Israel. Next slide, please. Thank you. So as has been said before, we are at the Department of Chemistry in Bar-Ilan, and my lab is part of a few organizations that I will very briefly present. I do have a few minutes, so excuse me for the very fast presentation. Next slide, please. So in the Department of Chemistry in Bar-Ilan, we do have 7 research groups working in energy. Mainly, we are working on electrochemical propulsion. So all the groups are involved in the electrification of the transportation, whether it's going to be through batteries or it's going to be through a vector that is green, like the green hydrogen.
And we do have 3 research groups working on hydrogen specifically in Bar-Ilan. One is a theoretical one. We're doing calculations to find the best components for the fuel cell and electrolyzer for the production and the use of the hydrogen. And 2 groups are working on the experimental application of hydrogen. So my group and the group of Lior Elbaz. And we do have in Bar-Ilan an umbrella that is called the Israel National Research Center for Electrochemical Propulsion. In short, it's INREP. This is the largest group of researchers working on the field of electrochemical propulsion. We are leading 7 universities. So 7 universities in France, it's not a lot. In Israel, it's 100%. So all the universities that do have some activity in science and technology are involved into this center that is led by Professor Doron Orbach, my colleague in Bar-Ilan. And this has been an endeavor of 10 years of research and development. And we do have a lot of collaboration with the French Institute of Research, the CNRS. Professor Taras Kohn, for instance, is part of is a board member of this center. Next slide, please. So I will talk about 2 things: the green hydrogen production and the way that you can use in power sources, mainly for fuel cell. And there's a third one that is a bit of maybe the obvious, that hydrogen will be used in conjunction with the natural gas. And I have an activity on sensing, which is something that is also related to safety. And sensing for the hydrogen will be really a challenge, because the hydrogen will be everywhere, and it will be mixed with other gases in some cases, like natural gas. And this is something that we're working on. But today I will speak about 2 examples of where we can help in terms of research, fundamental research, for the production of hydrogen and for its use. Next slide. So the main question that we have today is that we want to develop a technology that will be sustainable. So we want to be more clever than the previous one, but which it's not easy, because we don't have to rely on any critical raw materials. So this is something that we've been working on during the last years. So I present here a very brief overview of what we've done. We are working on electrolyzers. So electrolyzers is how to do water splitting using electricity. If you're using a green renewable source of electricity, then you're completely green. So we've been publishing a lot on the way that you can remove most of the critical raw materials from the electrodes that are used for the hydrogen production. The hydrogen is usually going together with the oxygen evolution. So we are working on both electrodes to develop the catalysis, which is based on non-critical raw materials. We do have a partnership with a lab in France, which is the LEPMI in Grenoble, where we do have some work that we can get some enhancement of the activity of the materials using electromagnetic field. And this is something that is a breakthrough, because you can really get more efficient system by a factor of about 20% more efficient than without using any kind of field. Next slide, please. So I'm going to present you one example of this kind of enhancement that you can do by slightly modifying the system. So I'm talking about electrolyzers. So this is you've got on the left side a very simple scheme of an electrolyzer. Usually what you're using is some aqueous solution. In that case, this is an alkaline aqueous solution that we pass through a device that is made of a membrane and 2 electrodes. And if you have one additive, which is a waste, in that case, we are using urea, which is also called AdBlue. It's an additive that is very simple. It's a waste. So simply by changing and adding this waste, you can get less power consumption. You get 200 millivolts less voltage for your electrolysis. And this is something that is based only on non-critical raw materials. It's based only on nickel in that case. We've recently published this work. So this is something that we believe will be the future of hydrogen, how to use waste in the device so that you can both use the waste. I mean, you know that you're doing something that is beneficial for the industry because you've got less waste, and also you're going to be using that to get more energetic and more efficient process. Next slide, please. So on the other side, once you get the hydrogen, then you need to use that. So usually you're going to use that in a fuel cell if you want to do some electrochemical process, which is more effective than burning the hydrogen. So if you're doing that, you're going to be building fuel cells, and the main components for the fuel cell in terms of cost is the catalyst and the bipolar plate. So these are the blue and the green that you see in the little square, in the little circle that you have on the left hand side. And so we've been working in reducing all the precious group metals, and now we are moving to single atom catalyst so that we can use really like 2 orders or 3 orders of magnitude less materials to do the same kind of reaction. Next slide, please. We are working on both PEM fuel cell and also alkaline fuel cell. Alkaline fuel cell is really some very good partnership that we have with the company Hydrolyte that we present in the afternoon. So in that case, we've been working a lot to develop the non-critical raw materials, and we have a list of achievements so that we are very proud to be part of this Israeli company as a research lab, and that's something that we are looking for. I mean, usually we do have a lot of research and development that is some joint partnership between the industry and the research lab in Israel. And this is something that we should do also across the borders between France and Israel. I hope that the next call for proposal will really promote this kind of activity. And with that, I would like to thank the research group. So the next slide is simply a picture of my research group. During the corona, we were not exactly 2 meters apart one from each other, but only for the pictures, and you can see some of the masks also in the end of some of the people. Thank you for that.
Thank you very much, David Zitoun, for your presentation. And we'll turn to conclude this panel with a second French laboratory, and with Dr. Jérémy Régnier. Jérémy Régnier, you are a researcher working within the Laplace laboratory, and notably on what you call the hydrogen platform, which was launched in 2010, and which assembled within Laplace the experimentations from other laboratories, including the CNRS that was mentioned by David Zitoun, the French National Center for Scientific Research. Can you elaborate maybe on your research?
Thank you, Ariel. Hello, everyone. My name is Jérémy Régnier. I'm an assistant professor at Toulouse INP University and researcher at the Laplace Laboratory, Laboratory of Plasma and Energy Conversion. So I will try in 10 minutes to draw a quick overview of major research initiative around H2 in the Occitanie region. I would like to note that this presentation has been prepared by Christophe Chopin, which is the researcher director with the National Center of Scientific Research, and Christophe apologized for his absence today, and I will try to be as close as possible to the message he wished to deliver. So next slide, please. So to introduce the activities of hydrogen in the Occitanie region, we first wanted to introduce the existence of current and future experimental platforms. Indeed, researches on hydrogen technologies require important experimental resources. Indeed, we need gas installation and equipment, electrical installation and equipment, thermal installation and equipment, security equipment. So different projects, mainly financed by the Occitanie region. We have now a 600 square meter platform dedicated to the experimentation of various applications employing hydrogen. For example, fuel cell application for land and air transport, or electrolyzer for hydrogen production. Around 60 researchers are involved in the life and in the operation of this platform. These partnerships include, in fact, 4 academic labs in Toulouse. Together, these labs have suitable complementarity concerning their areas of expertise to properly address the problematic relative to the use of the hydrogen energy in various applications. We can see that the 4 labs could emerge on electrical engineering for the Laplace, fluids engineering for the EMFT, chemical engineering for Laboratoire de Chimie Chimique, and material science for the CEREMAT. Okay, so next slide. Thank you. So, following the rapid development of hydrogen application and, in fact, the increasing demands of partnerships for industrial and academic projects, the construction of a new platform is planned. With a surface of 10,000 square meters, this project will benefit from financial resources for infrastructure and also financial resources for scientific equipment. The final delivery of the center is planned at the end of the year 2024. This platform will be organized around 3 main topics. The first one concerns a space dedicated to test benches of high power application and will allow tests under various operating conditions, for example, variation of pressure, of temperature, of humidity. The second one concerns a space dedicated to research projects with low power tests and specific instrumentation to favor experiences focused on the study of scientific and technological obstacles. The third one concerns a space dedicated to professional and student training around hydrogen technology. Moreover, the platform should be provided with an high-capacity electrolyzer to have an autonomy for the H2 production. Notice that this project already have a strong industrial support and interest, including the field of land and air transport application, for example. Thank you. Next slide, please. In association to the current and future platforms, several projects exist from the local to the national scale. An example of local project is a project called LICHI. It allows to the 4 labs previously mentioned to work together, each lab having its own area of expertise. The laboratory Laplace works on fuel cell and electrolyzer with diagnostic, aging, and system considerations. The EMFT works on modelization of transfer and hydrogen combustion also. The CEREMAT works on material and design of fuel cell and water electrolysis, and the lab of Génie Chimique works on gas network and H2 transport, and also on the design of aqueous electrolyzer. So all this skill in one place allows to address 3 of the main existing challenges for hydrogen, that is to say, the production of hydrogen by electrolysis, the storage of hydrogen, and the energy valorization from hydrogen. Next slide, please. Another example of project is the project Rio dedicated to green hydrogen. This region-wide research project is a federation of laboratory labs from the Occitanie region. The partnership ambition of this project is first to favor, of course, the emergence of innovative research projects concerning hydrogen technology, but also to develop new industrial and academic partnerships. In addition, the educational issue and the sociability acceptability of hydrogen are also addressed in this project. Next slide, please. The scientific terms and ambition of the Rio project is, in fact, to provide a full coverage of all the value chain of hydrogen energy. So the production hydrogen, the problematic of the hydrogen storage, the use of fuel cell to produce electricity, or the potential of the hydrogen combustion, but also the safety requirements associated to the hydrogen system, and finally, the societal aspect. So we can see in this context that each item of the value chain is associated to specific fields of research to provide an as complete as possible range of scientific and technical skills. Next slide, please. On this slide, we can see detailed exploration of the expertise areas of the different labs to, in fact, demonstrate that each of them could be involved in a collective dynamic despite their different skill. In this context, the multidisciplinarity approach is promoted. Next slide, please. The previous one. Thank you. So finally, we would like to report that the labs of the Occitanie region also emerge in a national project called FRH2, which is the French research network on hydrogen energy. In fact, more than a project, the FRH2 is a federation of French labs working on the hydrogen energy. This federation is in fact a privileged entry point to reaching the French community of hydrogen researchers. Once again, the benefits of such a federation is to guarantee an as large as possible discipline coverage from the material to the systems. In this context, notice that the proposed approach also includes important aspects for the achievement of hydrogen application, which are security, sustainability, and economic realities. In this context, studying state of health of the system, the aging behavior, and providing diagnostic functionality is of first order. So thank you for your attention.
Thank you very much, Jérémy Régnier. We'll have now a few questions from the audience that we'll take with Thilo Schoenfeld. Thilo? Can you hear me?
Yes, we have a first question for Professor Rothschild. Are there some problems or challenges in working at two different temperatures, 25 and 95 degrees? Electrode wear. How is the elevation of temperature obtained? Balance of energy consumed? Well, it's actually a couple of questions.
Yes, so that's a great question. It's definitely a challenge. Okay, like from the same cell, we flow low, intermediate, and high temperature electrolyte, and preserving the heat in each and every one of these steps is essential for the overall energy balance of the system. So it's definitely a challenge, but it's a challenge that the company H2Pro is meeting. Perhaps Ken will elaborate on this later on. What I can add on top of this is that as it happens, the high temperature reaction that we need high temperature to catalyze it is exothermic, so it's emitting heat. So if we can preserve the heat that is emitted within the system and generate enough heat, then essentially we do not need to invest in heating the electrolyte every time that we do these thermal swings. So that's very briefly the quick answer. For more details, I'm happy to explain after the webinar.
You actually have asked a question to Jeremy. If La Paz is open for international cooperation, like Horizon projects, Jeremy?
Yeah, you heard me? It's okay? Yep. Yeah. There is on the several projects presented, there is also a large part dedicated to international collaboration. But in this part of the presentation, I focus on the local, in fact, collaboration and national and local collaboration. But we have in the lab international collaboration on the thematic of the hydrogen. Yes, of course.
Now there's two more questions for Nicolas. Does ONERA study problems posed by the installation of hydrogen tanks in the aircraft? If you want to answer this first, this question, Nicolas. Can you hear us? Not sure.
Yeah, not sure he can hear. Maybe we'll get back to him afterwards.
Yeah, okay. Otherwise, I don't see other questions in the. No. In which case, I would propose that you continue, Ariel, with the third panel.
Okay, sure. Thank you very much to all our panel speakers, the scientist speakers. So we understand now here that hydrogen is a clean burning molecule that could become a zero carbon substitute for fossil fuels in hard to abate sectors of the economy, such as aviation. All the processes concerned, production, conversion, transport, and end uses. So to check now on first industrial achievements, let's hear from 7 Israeli and French companies. Each will pitch for 5 minutes. And we'll start with the Liebherr Group, a world-leading system supplier of the aerospace industry. Active in France since 1961, with their aerospace headquarters being there. Mr. Kader Ben Mashou, you're the head of product and technology strategy at Liebherr Aerospace Toulouse. You will present to us Liebherr contribution for H2 fuel cell. Please.
Yes, good morning. So do you hear me?
We can hear you well.
Okay. So, good morning, everyone. So I'm Kader Ben Mashou, the head of technology and product strategy for Liebherr Aerospace Toulouse. So I will start with a very short introduction about Liebherr Aerospace. If you go to the next slide, please. So Liebherr Group is a multi-sectorial group which is facing several challenges for the energy and environmental aspects by considering that can impact all sectors, including aerospace and ground transportations. So hydrogen in general, in particular, using fuel cell for hydrogen application is a key topic for Liebherr Group and seen as a promising solution to answer for different challenges related to the environmental aspects and also according to our product needs. And we are investigating on this technology from some more than 10-20 years in the frame of different R&D programs supported by the French government or by the European Commission. So here today we'll focus on what is done by Liebherr Aerospace in Toulouse. So if you go to the next slide, please. So Liebherr Aerospace Toulouse is the excellent center of Liebherr Group dealing with air systems and thermal management, which means all systems that support the main function in the aircraft, so pressurization, air conditioning, cooling aspects, ice protections, and so on. So we are addressing the electrification of the main systems for the aerospace needs by considering also mutualization with the new product lines, and in particular by considering a global approach to optimize the the energy management, and more specifically the thermal management on the different nodes, by considering also some new kind of sources, like and in particular green sources that can be provided by fuel cell. So this is the reason that we have launched a specific project, which consists to use fuel cells as main power source to supply the different major loads of the system. So I'm talking about the non-propulsive part of the aircraft, by considering mutualization aspects in terms of energy management. And we have developed some specific dedicated testing facilities in order to be able to make some dedicated tests by considering the complete chain value from the generation up to the load. If you go to the next slide, please. So what is specific to Liber Aerospace in terms of activities done internally? So we can consider that finally our contribution is carried out on two main parts. The first one is the compressor for the fuel cell. So based on the pedigree we have developed during the last 20 years for automotive fields in the first step. So because there's a real added value by providing some turbo compressor using foil bearings technology, which means no lubrication system, so no risk of pollutant of the fuel cell membrane, for example, and more compact system, so with some advantage in terms of capacity and weight saving. So we are using finally the same technology to provide a solution for aerospace, which was launched some years ago now. So for aeronautics application, so we are considering a more global approach. So Liber is in charge of the system aspect. So it means the complete system, including the fuel cell stacks, by considering the best way to integrate the system, in particular regarding the thermal management aspects, and in order to consider some recovery energy capability in order to use in a smart way the thermal management, the thermal energy generated by the fuel cell, for example, to be addressed for other needs on other system of the aircraft. In terms of power range, we are dealing with some power between 100 and 600 kilowatts. So it means non-propulsive needs for large aircraft applications and the propulsive application for smaller platforms. If you go to the next slide, please. So here the objective is clearly to demonstrate the capability to use fuel cell technology as a potential green source for aerospace application, by considering the fact that it should be also considered as a main power source, which it means in terms of certification aspects and so on, to consider the all criteria in order to be able to use fuel cell as the main power source for non-propulsive systems. So this is the reason that we have launched dedicated project by considering different challenges. One of them is to be able to take benefits on what was done in the past in other sectors, like automotive field, in order to take benefits on the maturity of the technology initially developed for automotive field, for example, in order to accelerate the roadmap, which consists to develop fuel cell technology for aerospace application, by considering, of course, the specific requirements due to the aerospace application. So we clearly believe that fuel cell systems can be clearly promising to be used as a dedicated energy power supply for non-propulsive systems. The second main challenge is also to consider the mutualization aspects with the other system, and this is the reason that we have to consider a global approach, in particular regarding the energy management. So we should not consider the ways to cool down the fuel cell itself, but we have to consider it in a more global picture on how the fuel cell can be integrated with the full non-propulsive system, and how we can manage the energy in general in an electrical and thermal point of view by considering synergies capabilities. And this is the reason that we have dedicated activities related to the energy management by considering mutualization capabilities, with some dedicated demonstration developed in the frame of a dedicated test bench, which was developed in Liber facilities. If you go to the next slide, and it will be, yes, my conclusions. So in terms of expectations, so here when the main mission is we need to reinforce the synergy between the sectors. We know that the pedigree on fuel cell activities is more mature on ground transportation system, and we have to take benefits of what was done in such activity, in such sector for aerospace needs. We have also to reinforce the links between different key players, so the PEM manufacturer, the system supplier, and with a strong link with the universities and research center. For example, in Liber Toulouse, you have a strong links and a dedicated project with the University of La Paz, for example. We had a very good presentation just previously. And we have to consider this global chain value in order to develop some optimized solution for aerospace needs. And for that, we are supported using different structural programs, like Clean Aviation, which is under preparations, and the first call will be launched in the coming months. And we will have some, I hope so, some dedicated activities on fuel cell, and to make a strong link between aerospace and other sectors in terms of mutualization, in order to support this challenging roadmap, and that will clearly really be a key enabler to reach the global objectives in terms of zero emissions targeted from 2035. It was a short presentation just to give you the main message from Liber. Thank you for your attention.
Thank you very much, Kader, for giving us an overview on how Liber explores fuel cells for aerospace applications. I remind the audience that you can ask questions to our panelists in writing. So please do so, and we'll address the question to them at the end of this panel, like the two previous ones. And second in line, and I see he opened his cam. Thank you. Second in line, Dr. Chen Dotam. Chen is the co-founder and chief technical officer of H2 Pro. Chen, Avner told us before about the research on ETAC water electrolysis. At what point the reduction of cost of renewable energies will enable low-cost production of hydrogen? And what's your expectation regarding H2 Pro commercialization of the technology, please?
Great. Hi. First of all, thank you for giving me the opportunity to present to you. Next slide. Seems to be.
Just a minute. Yeah. Go ahead.
Okay. So yeah, so I've already explained to you a little bit more about the technology, and if you want, you can find much more information in our Nature Energy publication. So I'm going to go much briefly on what the company did and achieved and its goals in the last years that we exist. So H2 Pro, in a brief, was established in 2019 based on the technology that we developed in the Technion. Today we are more than 80 employees, and the technology that the company is based on is very well protected by multiple IPs. Next. Basically, the goal of the company is to be able to deliver systems that will be able to produce green hydrogen for $1 per kilogram before the end of the decade. In order to achieve that, we plan to provide products that are going to be very efficient and lower cost. So regarding the low OPEX required for that, this was achieved by the high efficiency of the system, which means that it will consume much less electricity compared to conventional electrolyzers. And in addition, the system cost is expected to be significantly lower. And this is mainly because of the simplicity of the system, and especially the stack. I'll show it later briefly, but in general, our system is very similar to alkaline electrolyzers if you consider the entire balance of plant. But the stack itself, this is what we completely change and revolutionize based on the ETAC technology and make it much, much simpler. And we believe that this will allow us to be able to sell those systems at a much lower cost compared to what is a conventional electrolyzer can provide. In addition to that, because we generate the hydrogen and oxygen in two separate steps, it can be much safer, and it also allows us to produce the hydrogen at higher pressure. Next, please. So if you compare ETAC technology to PEM and alkaline electrolyzers, so the first and main difference is the low power consumption that comes, as Avner explained, by removing the oxygen evolution reaction or the electrochemical oxygen evolution reaction and replacing that by a chemical reaction, which does not consume power. This allows us to produce the hydrogen much more efficiently. Next. The technology was already vetted by multiple third parties, starting with the Nature Energy, of course, the journal. And then before the company started, we were deeply examined by Fraunhofer Institute that came and examined the technology before the company started as one of the requests of our investors. And lastly, in 2020, we won the Shell New Energy Challenge that also understood the great promise that the ETAC technology has for this field. In addition, the company has multiple very strong investors, including Bill Gates Fund, Green Foundation, ArcelorMittal, Yara, Hyundai, and so on. Very strong investors that really believe that this technology can make a significant effect on hydrogen production, or more specifically on green hydrogen production industry. Next, please. Next. So basically, our roadmap is going quite well, and we are scaling up our technology very fast. So when we started in 2019, we had a centimeter square electrode that we developed in the lab. By mid-year of 2019, we have our first system that shows that it can work automatically. In 2020, we developed two systems, one which used already multiple cells and was able to produce 100 grams of hydrogen per day, and the second one that was able to produce hydrogen at high pressure at 45 bars. Last year, we were able to demonstrate integration of these two abilities and already made a system that can produce hydrogen at 45 bars and already able to produce hydrogen at 1 kilogram per day. We are now at the final commissioning stages of 10 kilograms per day system, and are designing our pilot systems that are going to be at the order of 400 kilowatts. And our product, we are aiming for a large scale product, so megawatt level products. And we expect that our first products will reach the market in 2024, and will be at least 4 megawatt in scale. And as you can see here, through 2023 to 2025, we're going to continue to scale up our systems. Next, please. So we've gone a long way since our centimeter square electrodes. Today we already have our mini production pilot line, what we call the R&D line. This one is able to produce 10 strips of electrodes, each one 2 meter long and 4 centimeter wide in those paths, and has the capability of producing producing about 3 to 4 megawatt of worth of electrodes for the electrolyzers. Next, please. These are the systems, basically how they look like. What is known as M3 and M4. Actually, I see that there's a mistake here. M4 is expected to be by April this year. It's going to be operational. As you can see, basically it's all in a container, at least for this small scale, so both the balance of plant and the reactors. Next. If we look further to the pilot level, so the pilot level is already going to be multiple containers. We're going to have one container for the cell packs, one container for the power, and another one for the balance of plant. So this is under design these days. Next, please. And this is how we imagine our future products. Basically, we're going to have multiple containers. Each white container, as you can see here, will have what we call the stack or the cell packs, we name the ETAC cell packs. Inside of them, each one will be able to consume 2 megawatt of electricity and produce hydrogen accordingly. And we'll have one container for power supply and one container for the balance of plant. And this grows like 8 or 16 megawatt. This is going to be like our normal sizes that we are planning to sell. Next, please.
Last minute, please, Ren.
Yes. So we are now in the in design stage for our first factory in Tziporit in Israel, and it will start to produce our products in mid-23. Next. And basically, this is the last slide, our go-to-market. So initial field tests are planned for 2023, and first product in 2024, 2025 to get the full capacity, and by 2027 to have another factory already in place and to be able to reach our goal of $1 per kilogram of green hydrogen. Thank you.
Thank you very much, Ren. And for sure, we understand now your technology can help develop green hydrogen production very soon. And now going from H2 Pro to H2 Pulse with Cyril Gagnepin and Elvire Bregoli from France, which support companies to achieve their hydrogen projects and is part of the Toulouse Hydrogen Platform. We talked with the Laplace Laboratory before. Who and how do you support the projects? Please, Elvire and Cyril, go on.
Yes, thanks for this webinar and thanks for inviting us to speak about H2 Pulse. I am the executive assistant, and now Mr. Cyril Gagnepin, our CEO, will present H2 Pulse, will present our customized services and our specificities and strengths. So please, Cyril.
Okay, good morning, everybody. My name is Cyril Gagnepin. I'm the CEO of H2 Pulse. H2 Pulse was founded in 2020 and had 10 employees now, 8 PhD and 2 engineers for the technical management. It's important for you to understand that the particularity of H2 Pulse that we have signed a license, an exclusive license with the Toulouse Hydrogen Platform. Toulouse Hydrogen Platform was presented before, but it's a Toulouse Hydrogen Platform is like an academic laboratory working on hydrogens for 20 years. This association allows H2 Pulse to benefit from the knowledge of the platform seniors experts, and for our customer is very important. Okay, it's very important for you to understand this. So the goal of H2 Pulse is to increase the skill of our customer to accelerate their hydrogen solution. Our goal is not to build a product of hydrogen. Very important for you to understand this. We are the R&D on at the end we explained that the goal of H2Pulse, but now it's very important for you to understand that we must help our customer to arrive at build their solution. So for this, we have three major activities. First, next slide, please. So the first time we make a specific training, not academic training, it's not our business, specific training, theoretical and practical, because it's possible for us to, with our customer, to arrive in the platform to make a different test. And it's very important for our customer to practice on a real product. So, so this training is a specific request, for example, about humidification, about temperature, about fuel cell electrolyzer, a different topic, gas and liquid. It's important for you to know that on the platform we work about liquid on gas. On the next step, please. And after the second job of H2Pulse is the engineering. So in engineering, it's the same thing on the request of customer, different points. We work a lot of modelization because a lot of customers ask us help about the modelization, but we work about different for the factory, for the different fuel cell, electrolyzer. So with our PhD, we have a lot of know-how about hydrogen, and it's possible for us to make a specific engineering. So next step, please. And now it's important for you to understand it's our specific goal, because okay, we help our customer, but at the end we want to build a specific test tool for our customer. For us, specific test tool, it's possible is an algorithm, software solution, an electronic test card, why not, a test bench, on a different solution. For us, it's very important to understand the requirement of our customer and to make a specific product. It's important for you to understand this. H2Pulse, okay, we study, we help, we make a lot of training, but at the end, the strategy of H2Pulse is to make a specific test tool for our customer. So, in conclusion, it's important to you to understand that our goal is to participate in the acceleration and the implantation of the hydrogen in the world, and to help our customer for us. Right. Yeah, at the slide, you must see different test bench of the platform, and it's possible for us to go to the platform with our customer to make the training, to make a specific test. And it's very interesting because in the French, we are not a lot of point, or it's possible to make a physically test. Okay, many thanks. For me, it's finished. Many thanks for your time, and many thanks too for this possibility of presentation of H2Pulse. Bye-bye.
Yes, we really have access to a lot of fantastic equipment, and this is really our strength. And so please feel free to contact us. Our website is h2pulse.com. The website is in French as well as in English, so please contact us and we will reply to you. And if you have any need for being supported for your hydrogen project, please remember we are here at your service. Thank you very much.
Thank you very much, Cyril and Elvire, for your presentation, for the pitch. So now we understand storage is also critical when talking about green hydrogen development. Reaching a delivered hydrogen cost of $1 per kilo will require massive scale up in demand, as well as cost declines in transport and storage technologies. So Asaf Sayada is here with us today. Please, Asaf, put your camera on. You are the CEO of HydroX, and you claim the ability to reinvent hydrogen storage and reaching the famous Jules Verne vision. We'll go So we'll
yeah, I can hear you. I can hear you,
you can hear us. So Asaf, how are you?
Okay, sorry for the technical issues.
Okay, so you're the CEO of Hydrox, as I mentioned, and you claim the ability to reinvent hydrogen storage and reaching the famous Jules Verne vision. I let you elaborate on that, maybe. Quite an ambition.
Merci, merci Ariel. And as I promised, I do this in English, but I'd be happy to continue conversations in French. Hello everyone. I'm Asaf Sayed, as you said. I'm the CEO of Hydrox, this startup which is literally reinventing hydrogen storage. And as you very well said, in order to make Jules Verne's vision a reality, the whole industry needs to cope with a few technology challenges, and we've mentioned some of them in the webinar today. But I'd like to focus on one critical challenge, which is hydrogen storage. The current, if you could come back to the previous slide, please. The current technologies in the market, whether this is about compressed hydrogen or liquid cryogenic hydrogen, ammonia, etc., all the traditional technologies for storing and transporting hydrogen are very problematic. They're not energy efficient. They use dangerous materials, toxic, flammable, explosive, and they're definitely not green for most of them. And as a result, they are a real obstacle towards the this vision of a hydrogen economy. And next slide, please. The Hydrox has developed a disruptive technology which actually addresses these challenges. Without getting into too much details, we're talking about a catalytic reaction, which involves very simple materials and a very complex process and catalyst, which is a proprietary technology of hydrogen, of Hydrox. This is about a very advanced chemistry and materials engineering, a circular reaction, which we can go back and forth, storing hydrogen and into a very unique materials. We're actually storing hydrogen into something which is very close to water, or some kind of baking soda, actually, more specifically, which actually solves all the issues I mentioned before. So please, next slide. Number one, it's completely, and the process is very simple. I won't get into the details. We're a little bit late on schedule. So please, next slide. The process is, as I said, totally green, and the materials are totally green. You could actually drink the carrier of hydrogen, meaning that operation is very simple, no safety issues, no very high compression or very low temperature as in traditional technologies. Very simple and non-toxic, non-explosive, non-flammable material, which makes the whole operation completely different from what we are used to today. Next slide. And beyond being totally green, it is highly energy efficient. The whole temperature, as I said, and the pressure which are required to make this reaction happen in our systems are really minimal, and as a result, the energy efficiency of the whole process is pretty unparalleled in the industry. And next slide, please. Now back a little bit on the history. This technology has been developed for more than 30 years at the Hebrew University of Jerusalem. Academic research spinned off from the university to become a startup a few years ago, and mainly in the last 2 years, after some initial investments were made to the company, we started developing the technology. I actually joined a few months ago, only to take this company to the next step based on the very disruptive IP which is patented, and the scientific team of the company in our labs here in Jerusalem. Next, please. We're now supported by very, I would say, international partners and strategic investors, which include which were joined recently by CLP, the energy giant from Asia, as well that even more recently by EDF for renewables, Johnson Matthey from the UK, and other strategic partners which understand and also got the potential of this technology. Our plans going forward. We're planning, next slide please, to go to launch our first products into the market by the end of next year in 4 main vertical markets. The first one is traditional industry, which is the main market of hydrogen storage today. Renewable market, solar and wind, a domain where we are looking forward to deploy our products and pilots in the next few months. Facilities like data centers, backup solution for these facilities, green one, replacing the traditional generators, are another domain. And of course, last but not least, the domain of mobility, transporting hydrogen to fueling stations for vehicles, trucks, rails, and of course aviation are definitely a major domain of a potential business for us. That's in a nutshell about Hydrorex, and again, I'd be very happy to get into more advanced discussions in French as a native, a Paris native, in the next few weeks. Thank you.
Merci, Asaf. Thank you very much. It reminds us as well that if hydrogen were to replace natural gas in the global economy today, transporting and storing hydrogen would need more infrastructure investment, actually. So before we have 2 last presenter, so I'll turn to Mr. Gil Shavit, the co-founder and chief business development officer at Gencell Limited. The market of hydrogen and fuel cell technologies are advancing rapidly with a potential of $150 billion. So how does Gencell position itself on it?
Thank you very much, Ariel, and thanks for the people listening to us. If you can go to the first slide, please. We are talking about a company that is 11 years old. Last year got to the Israeli stock exchange market, starting with alkaline fuel cells that we inherited from scientists that came from the former USSR, from the space industry, and some patents that we'll later share with you about non-noble metal catalyst for the alkaline fuel cells that we are already manufacturing and deploying. And lately, we are dealing with ammonia as the hydrogen storage. And if you go to the next slide, we are talking about a way that after we have developed our alkaline fuel cells, we found out that one of the energy saving and energy condensed material is ammonia. And ammonia has some nice qualities. We know that ammonia could be toxic, but there is a way how to handle it with the surrounding of water. So after having an ammonia-based fuel cell, after we had the hydrogen-based fuel cell, we have started to develop a process to take renewable resourcing like solar and wind, and to go directly to green ammonia process that says you get water, you get nitrogen from the air. So it's water, air, and renewable power, and we get immediately ammonia. And then we have our ammonia cracker to bring it back to hydrogen and to generate back to the fuel cell as the power generator. So if we can go for the next slide, please, you can see that we are talking about a world that is moving to sustainable transportation, and we know that hydrogen is going to lead. So it looks like the whole webinar is dealing with that. So next, please. We're talking about a way how to convey very, very efficiently the hydrogen. So what we are talking about is trying to wrap the hydrogen in a much kind of more, if you talk about cost-effective and also effective way, is to wrap it not as a liquefied hydrogen at low temperature, but to convert it into ammonia. So if you can see next, we're talking about using ammonia, the NH3, and by our special patent that we started also to deploy now with cracking on the spot. So hydrogen with a special catalyst material is losing the connectivity to the nitrogen molecule, and then with a very small mass, relatively small mass of heat, we let the hydrogen leave. So N2 comes back to the air, hydrogen H2 gets to our fuel cell. So if you look to the next slide, please, for transporting it, you can take every ton of a single ton of ammonia can hold more than 2 megawatt hour. It's a 2.3 megawatt hour of energy to use by the fuel cell, net energy. So if you look at the size, it's a 1.2 cubic meter, and you have like a battery of more than 2 megawatt hour. So you can go later to the next one. So what we have here is the entire cycle from sun directly to green ammonia, very easy to transport, and then you can decide whether you want to fuel the airplanes by ammonia and crack it in the aircraft, or you can do the process. If you look at the next slide, we can do the process by that you have the ammonia cracked on the spot going to hydrogen, then it could be used by the aircraft, or also with the ground support systems that could be all green, all run on green ammonia that came from renewable resourcing. Then if you can go to the next one, it's key benefits. It's we overcome the cost and availability of that hydrogen transportation, because hydrogen, we can see several options to go into low cost hydrogen, green hydrogen. The barrier is the transportation and storage. And here we supply the solution with wrapping ammonia, the hydrogen as ammonia, and then cracking it on the spot with a very low losses. The endpoint, we can show already a very high efficiency and economic solution for the hydrogen future financial world. And thank you very much.
Thank you very much, Gil, and thank you for waiting as well. I know we are running a few minutes late. So now we'll conclude with Airbus. What about Airbus work now? You all know Airbus is a global pioneer in the aerospace industry, operating in the commercial aircraft, helicopters, defense, and space sectors. Airbus has the ambition to develop the world's first zero-emission commercial aircraft by 2035. And Frédéric Rigal works as an engineer on the Airbus strategy to minimize the climate impacts of the aviation sector. So Frédéric, you're the last but not the least of our speakers. Please, the floor is yours.
Yes, thank you, and thank you to all the speakers. So indeed, in Airbus, we consider hydrogen in the global context of the ways to minimize the climate impacts of aviation. And we know that there is no silver bullet for our sector, and we are conscious that our next big challenge is to deploy the multiple solutions that will lead to the net zero emission target by 2050. So in terms of aircraft technologies, operations in infrastructures, as well as low carbon energies, and we know that this low carbon energy have a very big role to play and a major role to play in this roadmap. So on the next slide, we show, sorry, it's the slide after this one. Yes. So on this slide, we show our vision for the deployment of the low carbon energies that combines the biomass-based fuels, which needs to be produced under strict sustainability criteria, with a very scalable power to liquid synthetic fuels, which are dropping fuels. So the SAF, sustainable aviation fuels, are dropping fuels, which are certified for use by the existing fleet of aircraft. So the PTL, the power to liquid synthetic fuel is ideally made on one hand from captured atmospheric carbon, which can also be permanently stored underground if we want to benefit from negative emissions. And on the other end, the PTL is made from hydrogen, which allows synergies with the development of an hydrogen economy and the ultimate use of hydrogen as a propulsive energy for our future aircraft. Thereby, aviation will be increasingly a consumer of low carbon power, and this needs to be properly anticipated. So on the next slide, coming back to hydrogen. So these are the three reasons why Airbus is seriously working on hydrogen for aviation use. So first, hydrogen is a zero emission energy, providing, of course, that it is produced from renewables via electrolysis notably. It does generate no direct CO2, and it has the potential to reduce also the non-CO2 emissions, such as NOx, as well as the impact of condensation trails. And our colleagues from Onera spoke about one of the multiple projects that Airbus is engaged into in order to confirm such benefits. So the second reason is the cost of producing H2 is likely to decline over the next decades as it gets widely adopted by various industries and as renewable power prices continue to fall. So this will make zero emission flying increasingly economical. And third, as we just said, hydrogen could be used as an ingredient of power to liquid synthetic fuels or consumed directly on board an aircraft, either through direct combustion or through fuel cells or through both. So on the next slide, just to close, on the next slide, yes, we would like to close with a few pictures of the three concept hydrogen aircraft that Airbus is currently exploring. They have a seating capacity from 100 to 200 passengers, covering ranges from up to more than 2,000 nautical miles with hybrid turboprop or turbofan engines. And of course, hydrogen systems such as a storage of liquid hydrogen and also distribution. So that's the last slide from my side, closing on nice aircraft pictures.
So thank you very much, Frédéric. Well, we now are many to expect we'll be able to fly Airbus zero emission by then. And we'll address a few questions from the audience with Thilo Schanfeld. Please, Thilo.
Yes, thank you. Well, the first question addressed actually to one of the first speakers of this panel, who was Chen Dotan. And the question was, do you think that your ETAC technology is also suitable and can be used by seawater? In which case, should it be desalinated first? Mr. Dotan, please, if still connected.
Yeah, so maybe Chen had another meeting, maybe Avner Rothschild is here to answer. But if not, we'll address the question later on.
Yes, I'm here. Can you just?
Yes, Avner, we can hear you.
Can you please just repeat the question?
Yes, sorry. The question was if you think that your technology, ETAC technology, can also be used with seawater, suitable for seawater, and in which case does it have to be desalinated first?
Well, currently our technology works on distilled water with the potassium hydroxide base. Yes. Actually, we don't have on our plan, on our focus, any plans to use directly seawater. I'm aware of a number of recent techno-economic analysis that indicate that the desalination adds a negligible cost to the overall cost of hydrogen production by water. So we do not focus on this direction at all. I don't know if we will change our minds. Maybe this will come up later. In principle, we do have advantage over conventional electrolyzers in using anything that is less than ultra pure DI water by the fact that we do not have a membrane in our cell. So a membrane is a delicate component in electrolyzers. It is also prone to fouling and other issues which we do not have, and therefore we do have advantage over conventional electrolyzer in this direction, but this is something that we currently do not pursue.
Okay, thank you. Now a question again in the chat box. I think it's addressed to Frédéric Rigal of Airbus. Are miniature nuclear plants such as molten salt reactors potentially competing solutions for aviation? Question asked by gentleman Alain Leray of French railway organization SNCF.
Your mic is off. You're on mute.
Frédéric?
Yes, can you hear me?
Yes.
Yes.
Okay. Well, in fact, we are not an hydrogen producer, but we are looking at the various technologies to produce hydrogen in order to properly assess the costs of the energy, which has a strong influence on the cost of operating an aircraft, as you know. So in terms of which kind of power could be used to produce green hydrogen, we are quite agnostic. What is important for us is that it's a low carbon hydrogen and that it is available at affordable costs. So of course, any low carbon power technology mature enough and available at low cost is welcome to produce large amounts of the large amount of green hydrogen that we will need for aviation.
Thank you. And the second question that to some extent goes into the same direction. Do you think that in the very long term long haul flights can also be powered by hydrogen? Because in which case you would need seems to be a high need of storage on board of hydrogen.
Yes.
So long haul flights as well.
So what I would say is that it's already possible for long haul flights, but on the form of power to liquid synthetic fuels. So for sure, very long haul flights for a long time will be powered by such liquid fuels, but which can be made from hydrogen. So it's more now a question of the form of the energy rather than onboarding the hydrogen on the aircraft by itself.
Thank you. Well, we are a little late. 15 minutes late. I don't see any further questions in the box and chat box. Maybe Ariel, if you want to close the session.
Let's conclude. I want, with all the organizers of the event, I want on behalf of all of us to thank all the speakers who participated in this webinar, all the presenters. We had high-level presenters. Next time we'll improve as well on a few women presenters, but we had a few women high-level presenters also in this webinar. So this webinar allowed us to understand that the French and Israeli approaches to the industrialization of green hydrogen and its application are certainly different, but can be complementary. The webinar organizers are also aware that this first French-Israeli event must be followed by others to help consolidate certain partnerships that could be beneficial for both parties. It is important to note that the France-Israel High Council for Science and Technology is organizing during 2022 a scientific symposium on hydrogen-based energy, reducing the use of carbon-based energy for reduced carbon dioxide emissions, and open to both French and Israeli scientists to enable them to respond to a call for binational projects that will be sent out shortly. So that's the first. And the second, the Israeli office, on a more commercial note, the Israeli Office of Business France organizes 2 missions this semester of 2022, currently open to French companies for registrations. First, a French aerospace delegation on the week of March 21. So feel free to contact me, for example, to have more information regarding this mission. And second, another Tech for Change acceleration program on green transitions, where innovative companies can apply for those 2 missions. So you can PM me. Last but not the least, I would like to thank all the organizers. Also thank Jennifer on the Aerospace Valley side for all her help on the organizing this webinar. And I wish everyone a good day. Bye.
Thank you, Ariel. Thanks for your professional moderation.
Thank you very much.
Thank you, Thilo.
Thank you. Bye-bye. Bon appetit.
Bye-bye.
Bye-bye.